Hello, this is Mr. Collier, and today we're doing DeMoivres Theorem, an exponential form of a complex number. Alright, so we have at the beginning here, we have a couple of useful properties of the modulus and argument of complex numbers, and we'll see some easy ways to prove that in a bit. First, let's take a look at DeMoivres Theorem. It states that cosine theta plus I sine theta all raised to the power of n equals cosine n theta plus I sine n theta. So that's DeMoivres theorem. We're going to prove it in two different ways today. First, we're going to prove it by induction. So let's start off with the base case n equals 1. And if we have n equals 1, let's look at the left-hand side first. It equals cosine theta plus I sine theta to the power of 1, which equals cosine theta plus I sine theta. The right-hand side will be equal to, that should be this there, cosine 1 times theta plus I sine 1 times theta, which equals cosine theta plus I sine theta. So they're the same, so therefore the result is true for n equals 1. Next, we'll assume the result is true for n equals k, where k is some positive integer. Okay, so that is cosine theta plus I sine theta to the power of k equals cosine k theta plus I sine k theta. Okay, so n equals k plus 1. We need to show cosine theta plus I sine theta to the power of k plus 1 equals cosine k plus 1 theta plus I sine k plus 1 theta. So that's our goal, and we're going to start with our assumption. Actually, we're going to start with this. So we're going to start with cosine theta plus I sine theta to the power of k plus 1. And in many induction proofs with exponents, we take the k plus 1 and we're going to rewrite this as cosine theta plus I sine theta times cosine theta plus I sine theta to the power of k. Okay, because this is an exponent of 1, and you add them together, you get k plus 1. So we rewrite like that, and we know what this is equal to by our assumption. So we can write that this is cosine theta plus I sine theta times, this is equal to this, so cosine k theta plus I sine k theta. And next we'll multiply these two brackets together, and we'll get cosine theta cosine k theta. Let's combine the real parts right now. I know when I do I sine theta times this, I'm going to get a real number. I'm going to get negative 1. I times I is negative 1. So I'll get sine theta sine k theta, and then the real part, the imaginary parts, are going to be cosine times sine here. You're going to have I cosine theta sine k theta, and here you're going to have plus, I'll write down here, I sine theta cosine k theta. Okay, so let's take a look at this now. Cosine theta, cosine k theta minus sine theta, sine k theta. Looks like a trig identity from the formula booklet. So let's take a look at the trig identities from the formula booklet. And that would be this one right here, right? So here we have a subtraction sign, so we do the opposite here. We're going to add those two arguments together. It's going to be cosine. And add these arguments together, you're going to have theta plus k theta. And plus I, we'll factor out the I, and then we have cosine, sine, sine, cosine. Okay, so that looks like this one, and it's addition, so we're going to add those arguments together. Same thing. This is going to be sine theta plus k theta. Okay, let me go back a second. When I did this step here, I should say by assumption, because that's when I use my assumption from before. Okay, anyway, I have this here, and then it's just a matter of factoring out the theta, and we'll have cosine of k plus 1 theta plus I sine k plus 1 theta, which is what we wanted. So therefore the result is true for n equals k plus 1. Okay, so we can say the last part, since the result is true for n equals 1, and assuming it's true for n equals k, implies it's true for n equals k plus 1, then, well, let's write it out. Cosine theta plus I sine theta to the power of n equals cosine n theta plus I sine n theta for all n in the positive integers. Okay, so that's the proof by induction. Next we're going to be using DeMoivres Theorem to find this quantity, and we're going to do this a couple different ways. So this is the complex number 1 plus I. This is the real axis, imaginary axis. Here's 1, here's 1I. So this is the complex number we're talking about, 1 plus I. We can see the argument here is going to be pi over 4, or 45 degrees, and root 2 is going to be the modulus. So we can write this statement here as root 2 cis pi over 4 all to the power of 6. Okay, so now using DeMoivres theorem, well, first let's do root 2 to the power of 6 is going to be 8. And using DeMoivres theorem, we're going to have cosine of 6 times pi over 4 is 3 pi over 4 plus I sine 3 pi over 4. Okay, so actually, sorry, 3 pi over 2 we're going to get here. Okay, so 3 pi over 2 is right here. That's 3 pi over 2. So the sine value here is -1, and the cosine value here is 0. So this is gone. This is going to be 0. So we're going to have just 8 times I times -1, which equals -8I. Another way to do it with in Cartesian form is we can write this as 1 plus I squared to the power of 3. And 1 plus I squared, you're going to get 1 plus 2I plus I squared, and you're going to get 1 plus 2I minus 1 cubed, which equals 2I cubed, which equals 8 times I cubed, which equals 8I squared times I, and I squared is -1, so we're going to get -8I, same thing. Alright. Next, we're going to use our calculator to calculate a couple of these quantities. So let's take a look how we can do complex numbers in our calculator. First you need to go to mode, and let's keep it on radian mode, and down here change it from real to a plus bi and press enter, and now we're ready to do some complex numbers. We can check our answer from here. Okay, so if you type in 1 plus I, 1 plus I to the power 6, you see you get negative 8I like we got manually. Now we can type this quantity in, so e is over here, e to the power of, e to the power of I times pi divided by 3, and we get this quantity. So it's 0.5 plus 0.866 about, approximately, I. Okay, that's approximately equal to that using our calculator. But you might notice this is half, and this quantity here is actually root 3 over 2I. Okay, so we can do some similar things here, but in general, what you get is e to the power of I theta is always equal to cosine theta plus I sine theta. Okay, so this is called Euler's formula, and we're not going to prove it right now, but you can prove it later with some more advanced math. So that's Euler's formula. So something interesting happens if you take Euler's formula and you substitute in the angle theta equals pi, then what you get is e to the power of, I pi equals cosine pi plus I sine pi. Cosine pi, well, pi is over here, is equal to, well, the cosine of pi is negative 1, and this is going to be I times 0, which equals negative 1. And what you get is, right over here, what you get is e to the power of I pi equals negative 1, or e to the power of I pi plus 1 equals 0. This is a very famous equation called Euler's identity. Okay, a lot of people really like this formula because there's 5 of the important mathematical constants, e, I, pi, 1, and 0 are all in there. Okay, so now you can write any complex number as r e to the power of I theta. It's always going to be equal to r cis theta. Okay, so the same thing. And depending on what we're doing, one of these forms could be more useful than the other one. Okay, so now we have the 3 forms. This is Cartesian form. Sometimes that one's the most useful. This one's modulus argument or polar form. And this one is exponential, or sometimes called Euler's form. Okay, and you can switch between them with formulas like this and such. Okay, it's very easy to prove DeMoivres theorem using Euler's formula. So you can just say, for example, cosine theta plus I sine theta to the power of n equals, this is the same as e to the power of I theta to the power of n, and this simply equals e to the power of I n theta because of our exponent laws. And we know that this is equal to cosine n theta plus I sine n theta. So we're done. It's a very easy proof with Euler's formula. Find the real and the imaginary parts of this this complex number. So we can rewrite this as 4 times cosine 2 plus I sine 2. So the real part of z equals 4 cosine 2. That's not an exact value, so let's just leave it as 4 cosine 2 And the imaginary part of the real number is 4 sine 2. Okay, this one, let's first draw a diagram to see what quadrant this is in. So this is 3 on the real axis and negative 3 on the imaginary axis. So it's over here. And this angle here is going to be, or I should say the argument is going to be negative pi fourths. And the modulus is always root this squared plus this squared. 3 squared plus 3 squared, which equals root 18 or 3 root 2. Okay, so that's 3 root 2, and to write it in trigonometric form, we can say that z is 3 root 2 cis negative pi fourths. In exponential form, we can say that z equals 3 root 2 times e to the power of negative pi over 4i. Okay, so we can write it in those forms in that way. Use DeMoivres Theorem and the binomial theorem to show that cosine 3 theta equals this. So we're going to prove this identity. And we can use DeMoivres Theorem and binomial theorem to do so. This is a very common type of question, and you can do the same thing with cosine 5 theta or 7 theta or whatever you want. You can make lots of different you can prove lots of different trig identities using DeMoivres Theorem. So notice here we have a 3 theta, and we want to use DeMoivres Theorem, so that means we're going to start with cosine theta plus I sine theta to the power of 3 to get this one. Okay, so if we do that, we get cosine 3 theta plus I sine 3 theta using DeMoivres Theorem. Okay, but we also know that this quantity is equal to, if we use binomial theorem, and let me just write this out. So if we expand using binomial theorem, we're going to have cosine cubed theta plus 3 cosine theta I sine theta plus, oops, that's not quite correct, sorry, 3 cosine squared theta I sine theta plus 3 cosine theta I squared sine squared theta plus 1 I cubed sine cubed theta. Okay, so now we have, let's look at the real parts here. Cosine cubed theta. This is not going to be real. This one's going to be real because I squared is negative 1. So now I squared is negative 1. We're going to have negative 3 cosine theta sine squared theta plus I times, this is going to be 3 cosine squared theta sine theta, and this is going to be minus I, right? It's going to be I squared times I. It's going to be minus I, oh, the I is already factored out, sorry. So it's going to be minus sine cubed theta. So that's what it simplifies to here. And next, we need to just equate the real parts, okay? So equating real parts yields, we get, so this is the real part of the left-hand side, this is the real part of the right-hand side, so those must be equal, which is what we set out to prove anyway. Sorry, this should be equal. Cosine cubed theta minus 3 cosine theta sine squared theta. Okay, so that is the proof of that. Okay, one more question. Here we're going to divide two complex numbers raised to the power of n. So let's go ahead and do that. So z1 over z2 to the power of n equals, so we're going to be dividing these moduli, and here, when we divide cis, we subtract the arguments. 3 pi over 2 minus 2 pi over 3. Okay, we subtract them because it's easy to see that if we look in exponential form, if we have e to the power of I 3 pi over 2 divided by e to the power of I 2 pi over 3, since we're dividing exponents here, we just subtract the exponents. Yeah, we're dividing these, we'll subtract the exponents. So that's why the arguments are subtracted here. Okay, but the 2 root 3 divided by 2, that's going to be division here in our equation. So we're going to have 2 root 3 over 2 gives you root 3. And this is going to be cis. Let's get a common denominator of 6. So this is going to be 9 pi over 6 minus 4 pi over 6, which is going to be root 3 times cosine. Well, I forgot the power of n. Hang on a second now. So this is all to the power of n. This is all to the power of n. So this is going to be to the power of n here. Cosine 5 pi over 6 plus I sine 5 pi over 6 all to the power of n. And next we can use DeMoivres Theorem to distribute this n, and we're going to have cosine 5 pi n over 6 plus I sine 5 pi n over 6. So the question asks us, what's the smallest positive value of n for which this complex number is a positive real number? So this is complex right here. The only way for it to become a positive real number is for this quantity to become 0. So this has to be 0, and this one is going to have to be positive for us to create a positive real number. So let's take a look at this. When is sine equal to 0? Well, sine is equal to 0 here, and sine is equal to 0 here. But cosine is only equal to 0 right here. So we're talking about this angle, which is going to be equal to 0 or 2 pi or 4 pi. So it's going to be some multiple of 2 pi. Okay, so if we want this argument to be a multiple of 2 pi, so let's take a look at it. 5 pi divided by 6 times n. If we want that to be a multiple of 2 pi, then n has to be, well, if n is 6, then the 6's will cancel and we'll get 5 pi. But we don't want 5 pi, we want a multiple of 2 pi. So n, the smallest value of n has to be equal to 12. Okay, if we have 12, we get some canceling here. And 12 divided by 6 gives you 2, so you get 10 pi. So that's the smallest value of n that gives you a real number.